Hello and welcome back. Chem 131, Chemistry for Engineers. And this is Chapter 7, Part 2. We're on slide 15, and we're going to be talking about coordination numbers. We're still talking about crystalline structures. And these are, and a coordination number is the number of atoms that are immediately adjacent to any given atom. Okay, so what does that mean? If this is the atom that we're looking at right here, this is atom, I'll shade it in. This is the atom that we're looking at. It's immediately touching this one and this one and this one and this one. So it's immediately touching 4 atoms, and that gives it a coordination number of 4. Okay, so one of the things that you'll need to know is you'll need to know a simple cubic structure has a coordination number of 6. A body-centered cubic structure has a coordination number of 8, and a close-packed structure, either CCP, cubic close packing, and HCP, hexagonal close packing, have a coordination number of 12. Okay, so as coordination numbers increase, each atom in the lattice interacts with more nearest neighbor atoms, as we call them. Okay, so the attractive forces of these interactions hold the crystal together. So that means that the higher the coordination number, the stronger the crystal. Okay, so a close pack structure, either a cubic close pack or hexagonal close pack, with a coordination of 12 is one of the most common crystal structures. Again, the more atoms you're touching, the stronger those attractive forces. And that makes it a very, very stable compound. All right, we are on slide 16. Okay, and this just shows you some examples of some of your preferred lattice structures. If you can't see all of this, remember that these PowerPoint slides are all in Brightspace, so you can go to them and you can look up one specific slide if you want to see it. But you can see here that as we're looking, I see a lithium right here, and you can see right here you have body-centered cubics, and your body-centered cubics are here. Okay, it's your alkali metals and a couple of alkaline earth metals. You have a block of your body-centered cubics right here in your transition elements. Okay, you have europium here. Okay, and that's so you actually don't have that many of them. All right, now let's take a look at another one. You have your simple cubic structure right here. And simple cubic structures are also not super common. You have samarium here. Okay, and then you also have boron and oxygen and fluorine. And you have mercury here. And then you have polonium here. Okay, and then that's pretty much it for those. Okay, and now you can see it's a slightly different color. Let's go ahead and look at over here you have a rhombohedral structure right here, and the rhombohedral is a slightly different one, and that's your arsenic, antimony, and bismuth right here. Okay, now let's take a look at your face-centered cubics right here. All right, now these are kind of a light blue color, and here's your face-centered cubics, your calcium and your strontium. And then you have this block in your transition elements, ruthenium, iridium, over to gold, up to copper and nickel. And then you have this aluminum, silicon, and germanium. You've got a few of these face-centered cubics. And then you have lead here. Okay. And then you have this block over here, neon down to radon. And over here, your cerium and thorium, Ce and Th. Okay. All right, now let's take a look at another one. We have and then I'll go ahead and you can look at these more, but that gives you some of your most common ones in there. I guess the other one that's very common in here, let's go ahead and we'll call this look at the hexagonal closest packing, and you can see a ton of them that are hexagonal. You've got your hydrogen up here and your beryllium and magnesium, and then you have this block here, starting with scandium in your transition elements, and then here. So you'll see that you've got this, and then zinc and cadmium, lots in your transition elements. So your hydrogen and helium are here, carbon and nitrogen, the selenium and tellurium. Okay. And then you've got a bunch of them down here as well. And your last one in here is this orthorhombic in your kind of your lavender purple colors. Okay. All right. On to slide 17. And slide 17 is looking specifically carbon structures. So let's take a look at our carbon structures here. Carbon atoms in diamond are joined by covalent bonds in a tetrahedral geometry. So remember, in methane, we had that structure here that looked like that for methane. But let's imagine then that what we're doing is we're actually, instead of having hydrogens there, we have carbons. Okay. And now that one goes out to there. And then you can actually, you come up here to another carbon and carbon and carbon. Okay. And then here, you can see how these work. So we can come up to a carbon, and a carbon and a carbon, and here we'll come out to a carbon and a carbon and a carbon and a carbon. And you can see you have this perfect a tetrahedral structure where instead of having methane, you have another carbon, and it just kind of goes on forever. And that's what makes these, you have these diamonds that grow and become this really, really amazing thing. Okay. Carbon has a lot of covalent bonds. It's basically never ending covalent bonds, which is why diamond has such an amazingly, ridiculously high strength. Okay. Now, carbon atoms in graphite are different. Carbon atoms in graphite form these hexagons. See, here's a hexagon attached to another hexagon, attached to another hexagon, attached to another hexagon. So this is what graphite is. They form these hexagonal sheets. Okay. And then you have basically the bond between the sheets is an intermolecular force, okay, which is what we'll be talking about a little later. Okay, so these are held together by your intermolecular forces rather than actual bonds. Okay, so what that means is that the sheet itself is very strong, but between the bonds isn't so strong. And that's what allows these sheets to slough off your pencil. Okay, so the sheets separate easily, which allows them to be used in writing utensils. So every time you write on your paper, what you're really doing is depositing a layer of carbon sheeting. All right, now let's take a look at metallic bonding. So in metallic bonding, we have what's called a sea of electrons model. And that basically means that this first square here, this is, we'll call this like basically a square of our metal. Okay. So all of the nuclei are lined up neatly in whatever they're in, that cubic packing, body-centered packing, hexagonal packing, like whatever our metal is, that's what it is. And then this blue that you can see around it is a sea of valence electrons. So you've got your nuclei there, and then in the middle here you have a sea of valence electrons, whatever your valence electrons are, and move pretty much as like throughout. And that actually allows them to conduct electricity. Okay. And it's also what allows them that if you apply a force here, you can get this to deform. And that's what allows your metals to be malleable and ductile. Okay. So let's take a look at a little bit more in this. Actually, I'm taking a look here, and I see that I have a note here to add in. Okay, so I said that they makes them malleable and ductile. So first of all, let's go ahead and define those. Malleable, I don't think I have this on my next slide. Okay. So malleable or malleability means malleable is the ability to shape something into something else without breaking. So that's what malleability means right here. Okay. And then we'll add in here we have the term ductility, and I'll go ahead and identify that up here. Ductility is it's the mechanical property. I should have put this on the slide, huh? It's the mechanical property describing the ability to be drawn into long, thin shapes or wires. Long, thin. Right? And that's that ductility there. Okay. And then conductivity, you understand because conductivity, we already understand that when we've probably already done a lab in the concept of conductivity and the ability to basically conduct electricity. Okay. Now let's talk about band theory and conductivity specifically. In band theory, what we have is we have the idea that electrons fill the lowest energy band first. Okay, and remember this lowest energy band, or we could call this the lowest energy level. Remember those N values. So that's just a review from chapter 6, I think it was. The band populated by valence electrons is the valence band. Okay. And the empty band above the valence band is called our conduction band. And the energy, you'll see pictures of this in a minute in the next slide. Okay. The energy difference between the valence and conduction band is the band gap. And last, we have that current flows when electrons move from the valence band to the conduction band. And the thing to remember here is that conductors have very small band gaps or no band gaps, or none, we'll say. Okay. And then insulators here, insulators have very large band gaps, and that large band gap prevents the electrons from actually crossing it. Now, semiconductors have band gaps that are intermediate. So between there, so they're not small and they're not large, they're in between. All right. So let's take a look at our band theory. All right. And left you space to sketch this out for yourself. Please do so. I wanted you to sketch it so that it's really in your brain. So this should be, you need to sketch this out on your sheets. And the thing here to look at is, so here we have a metal. And remember that a metal is also can be known as a conductor. Okay. And in that case, notice here that you have no band gap. Up here at the top in each one of these, you have This blue at the top is your conduction band. Okay. And then we have this green at the bottom is your valence band, remember? Okay. So because there's basically no band gap here, electrons can move pretty easily back and forth. Now, in a semiconductor, and you might also call a semiconductor a metalloid. So here I've gone backwards. Semiconductors are metalloids, the kind of that in between state. And you'll see here that you have an intermediate band gap, okay, or a small we'll call it a small to intermediate band gap. Okay. And that means that you can trigger, so electrons have to make this jump in some way. So then the question is how? And that'll be in a future slide. All right, now our next one over here, we have an insulator, and insulators are going to be nonmetals. Okay, and here you can see that you have a very large band gap. And that means that our electrons are going to stay in our valence band, and they're not going to move into the conduction band. And that's why insulators don't conduct electricity. In order to make semiconductors more able to conduct electricity, what we can do is we can modify their conductivity through something called doping. Okay. And when we're doping, we're adding controlled trace amounts of an element to a semiconductor to modify its properties. And there's a couple of different options for this. The first one is N-type. And when you think N, you think negative. And what you're going to do is you're going to be doping with a valence electron rich element, and we would call that negative. And one way to remember, like, is that your N types have more than 4 valence electrons. So they could have 5, 6, or 7 valence electrons, and that would make an N-type. So that's what you're going to be doing. You're going to be looking at your periodic table and saying, okay, well, how many valence electrons does it have? The the extra valence electron fills what's called a donor level just below the conduction band. Okay. All right, now let's take a look at p-type doping, and P for positive. And this is going to have a valence electron deficient element, and that means it's going to have less than 4 valence electrons. Okay, so that means that it could have 1, 2, or 3 valence electrons for a P or positive type doping. Okay, the lack of valence electrons creates what's called an acceptor level just above the valence band. Okay, so the valence band that you do when you create this acceptor level, you'll create vacancies in the valence band, and we just call those holes in the valence band. So this is kind of a picture of that. Here on slide 22, we can see an example of N-type doping. Okay, so phosphorus, remember, has 5 valence electrons. Okay, and that means that we're going to be doping N-type. And we take the extra valence electron and it fills what a donor level. And so here's our silicon, and here we have our band gap in silicon. And this is big enough, it makes it hard to get from here to here. So what we're going to do is we're going to put a little bit of phosphorus in it, and it's going to put a donor level right here. Okay, it's going to put this donor level here, and that way the electrons can move from the donor level into the conduction band. Okay, so just kind of remembering here, we had up here in the blue is our conduction band, remember from before, and in green here is our valence band. It's hard to see that. Made it match too much. So valence band here. Okay. And that's how we make silicon more conductive with an N type, such as phosphorus. Right. So now what we're going to do is we're going to do some P type doping. And in p-type doping, remember we have less than 4 valence electrons from before, okay? And so an example of that might be aluminum. Aluminum has 3 valence electrons, so it's a common p-type dopant, okay? And what that does is that creates this acceptor level right here. And then you can push extra electrons into the acceptor level, creating these little holes in the valence band. And it's easier to get them into the conduction band up here, again, to make them more conductive. So let's take a look at this. This should be really pretty easy review. First of all, it's asking, is this, are we going to be an N type or a P type with each one of these? And honestly, I'm going to do the same thing down here, and we're going to say N or P with each one. Okay, so gallium has 3 valence electrons. So it's going to be a P type because it has less than 4. Okay. And arsenic has 5 valence electrons, so it's going to be N type. And phosphorus also has 5 valence electrons, so it's going to be N type as well. Okay. Now let's come down here. We already did arsenic and phosphorus, so we won't do them again. We know that those are going to be N type. Okay. Now let's look at gallium. Gallium has 3 valence electrons, and then germanium has 4 valence electrons. So that makes germanium with 4 valence electrons. This is actually its own semiconductor, or metalloid. Okay. So this is not going to dope. Okay. But gallium at 3 valence electrons is going to make a p-type conductor. And that's how you figure those out, not too difficult. Let's add in some intermolecular forces. And intermolecular forces are the attractive and repulsive forces between molecules. They are not bonds. Okay, they are forces between. So even if we use the word bonding, we're not talking about bonds because these are between molecules. So they're forces that hold the molecules together as solids or liquids, but they are not actual bonds. And they are weak compared to bonding forces. Even the strong ones are weaker than bonding forces, and some are much, much weaker than bonding forces. Intermolecular forces are largely responsible for determining the structure and properties of condensed phases. And condensed phases are liquids and solids. Okay. And some examples of that, we have dispersion forces, we have hydrogen bonding forces, and I'm going to go ahead and put the third one in here because there are 3. So that's our first one and our second one. And our third one that we'll list here is what are called dipole-dipole forces. So this is this is showing the same type of thing that we showed before when we were looking at graphite. And remember, we had graphite in those hexagonal shapes here. Well, now you can see it in its structure here, where every point is a carbon on all of these points. And you can see here, you can see your double bonds that are here and here and, oh, sorry, here and here, not there in the middle. Okay. All right. And what you can see here is that you have the space between the sheets, and these sheets are held together through intermolecular forces. Okay. And these are just carbon atoms here. Okay. And so they're going to be our dispersion forces. And okay, there we go. So each one and what they're called. First of all, here on, oh, you know what? I forgot to put it in. This is slide 27. Okay. Dispersion forces are common to all molecules, and they are sometimes referred to as London forces, London dispersion forces, and sometimes instantaneous dipole induced dipole forces. An instantaneous dipole occurs when a fluctuation in electron density for an atom or molecule produces a dipole. So all of a sudden, two things line up just perfectly to create a little dipole. But these instantaneous dipoles are very short-lived, and they're constantly forming and reforming and disappearing, and they don't stick around. So London forces aren't very strong. Right. Here we are. We're still talking about dispersion forces here in slide 28. And now we're looking at induced dipoles. And we can induce a dipole by creating an external electric field. And what this does is it basically forces things to line up. So here we have just a plain old atom here. Okay. And then when we apply an external electric field, it distorts the atom and sort of pushes it like this so that you'll have a positive and a negative side. And then what happens is that you could even draw another one here, is that another one will line up here, and then you'll have another one lined up here with a delta negative, delta positive. And so they temporarily will line up. So you've got your positive hooking up to your negative and a positive hooking up to a negative here like this. And they temporarily will line up, and that kind of holds them together. Okay. So again, we're still talking about our dispersion forces here. So the strength of dispersion force can be estimated from the polarizability of a molecule. And polarizability is basically just a measure of how susceptible a molecule's electron density is to external fields. So the larger the molecule, the more polarizable it is, and the more susceptible it is to the electron density of your external electric fields. Okay. Now, we're looking at, this is our second type of one here. Well, it was listed third up there above. So this is a brand new type. It's called a dipole-dipole force, and this is another intermolecular force. So we'll say, I'm just going to start it like this so that you understand that this is not a dispersion force. Okay, so this is another type of intermolecular force, a dipole-dipole force. And these are the attractive or repulsive forces for molecules with a permanent dipole. It has the charge at the poles of a dipole is a fraction of the charge on an actual electron. So these forces are weaker than a chemical or an ionic bond. Okay, the larger the dipole, the stronger the dipole-dipole forces. And dipole-dipole forces are stronger than your dispersion forces are. So let's take a look at an example of that. If you look at carbon monoxide, go ahead and come down here. If we look at carbon monoxide, it's we have our carbon here, and it's triple bonded to our oxygen like so. Okay. And our the electronegativity for carbon is 2.5, and the electronegativity for oxygen is 3.5. So that makes our carbon, that means that what we have here is we have a carbon oxygen with a delta positive here and a delta negative here. And so that makes it very easy for them to link up. So you'll end up with this dipole force here that's linking your delta positive with your delta negative. Okay, let's look at our intermolecular forces now. That's our strongest intermolecular forces. And our strongest intermolecular force is hydrogen bonding. And it's a special case of dipole-dipole forces. They're very strong compared even to dipole-dipole forces. They're not quite as strong as bonds, however, but they get as close as you can without being an actual bond. They tend to occur in when you're connecting to fluorine, oxygen, and nitrogen. Now, fluorine has an electronegativity of 4.0, and oxygen has an electronegativity of 3.5, and nitrogen has an electronegativity of 3.0. Sometimes people will consider chlorine also with an electronegativity of 3.0 to have weaker hydrogen bonds as well. But your core ones here are fluorine, oxygen, and nitrogen. Oh, I don't know if you can hear the thunder, but my goodness. Okay. How would we do that in Washington? All right. Sorry, I had to duck out for a moment because it's thundering and bringing children and dogs in the house. Okay. So bonds are especially no, I already did that. My apologies. Okay. So what we're doing here when we're dealing with these hydrogen bonds is you have these really big, because hydrogen, remember, has an electronegativity of 2.1. So you're dealing with electronegativity differences of 0.9 and above. And that's why it only happens with these 3/4 elements, is because you have to have almost a whole point difference in electronegativity. Okay, so let's go ahead and take a look at some examples of this. One example of this would be hydrofluoric acid. Hydrofluoric acid has such strong hydrogen bonding that even though it's so strong, it's an incredibly weak acid because it does not want to come apart. It doesn't want, the fluorine and the hydrogen don't want to separate. It doesn't want to come apart from even its hydrogen bonding outside of its molecules. And so very little of it actually dissociates. And it's considered just a weak acid. That doesn't make it not dangerous. Hydrofluoric acid is one of the most dangerous acids out there, even though it is a weak acid, because it doesn't come apart, what it will do if you get it on your skin is it will actually burrow through your skin until it hits calcium, and the calcium in your body is in your bones. So if you get a drop of hydrofluoric acid on your skin, it will burrow through your skin until it gets to your bones, and then it will decalcify your bones. Very fun. And it's not good at all. So if you're ever working in the semiconductor field, they use hydrofluoric acid in a department called etch. And some of you might end up in the semiconductor field and you will learn never, ever, ever to touch the hydrofluoric acid. The only way, if you get a tiny bit on you, they will put a calcium cream on your skin. If you get a lot on you, they will rush you to the hospital and give you an injection of calcium. And it's not damage to the bones from hydrofluoric acid spills is not something that is reversible. So it is a very dangerous acid, even though it is weak. And it is HF, and the Lewis structure for hydrofluoric acid looks like this. Okay, so you've probably already drawn that and many times. Okay, and then we have, okay, and what will happen is you'll get another one here like this lining up. Okay, and we know from above that the electronegativity of our hydrogen here is 2.1 and fluorine is 4.0, and then 2.1 and 4.0. Okay, and just as the hydrogen is very attracted to that fluorine, you'll get an attraction here for your hydrogen bonding as well. Okay, let's go ahead and look at another one. Another common one is the forces that we find in water, and this is really important for liquid water and solid water because solid water forms a hexagon. It actually is one of the only compounds that increases its volume when it goes from its liquid form to its solid form, and that's in part due to these hydrogen bonds. Okay, so when you have H2O, what you have here is you have hydrogen bonded to oxygen, and oxygen is 3.5 and hydrogen is 2.1. So that gives it an electronegativity difference of 1.4, not as high as the 1.9, but 1.4 is still really pretty high. Okay. And so it'll always line up so that the electronegative oxygens are semi-attached to oxygens. Okay. Okay. And that's it also makes water a very fascinating substance with very strong intermolecular forces. So let's take a look at the intermolecular forces in each of the following. Okay. And so let's start with our CH4. CH4 looks like this. We have carbon attached to 4 hydrogens, just like so. Okay. Now you can see there's nothing special in this molecule. There's no hydrogen bonding with the carbon because that's going to be a pretty purely covalent bond. And you have no dipoles in this either because all the electronegativity differences here are 0.4 or less. So this only has one form of bonding, and that's dispersion forces. Okay. That's its only intermolecular force. Okay, so now let's take a look at CH3F. Okay, so CH3F has this methyl group on it. It looks just like the methane does over there, except we're going to replace one of the hydrogens with a fluorine. Now, fluorine, this is going to be different. Now we're definitely going to have a dipole because carbon is 2.5 and hydrogen is 4.0. So that means that this one, because it has a dipole right here, okay, that means that we are going to have two different kinds. You always have dispersion forces. Now we're also going to have dipole-dipole forces. Okay, now let's look at our last one here. We have CH3OH. All right, this is our methanol, and it starts with a methyl group here. Okay, and then it attaches to an oxygen, and then it attaches to a hydrogen. Now we have our oxygen attached to our hydrogen right here. And oxygen is one of the special atoms that, when it's attached to hydrogen, forms our hydrogen bonding. So this one will have dispersion forces because dispersion forces always exist. And it will also have hydrogen bonding forces. Okay. Okay, let's take a look at vapor pressure. In this case, we can see the vapor pressure is the gas phase pressure of a substance in a dynamic equilibrium with the pure liquid in a pure substance. Okay, so what here is strong intermolecular forces. Um, and that means that they'll have lower vapor pressures. And liquids with high vapor pressures are described as volatile and they have weaker intermolecular forces. Okay. So this is a very low vapor pressure. So it's going to have strong intermolecular forces and a low vapor pressure. This one is called volatile. It's volatile because it has a low boiling point. And you can get or low flash points, and you'll get liquids that will boil at or below room temperature, which can be dangerous depending on what you're working with. And so here we have weaker intermolecular forces. And those weaker intermolecular forces give you a high vapor pressure. Okay. Means so our in a strong intermolecular forces you only get a little bit of vapor pressure and a little bit of your molecules escaping to be vapor, and then in a volatile liquid with weak intermolecular forces you get a lot of escapage even before you hit your boiling point. And this is just a little chart here. You can see that vapor pressure and boiling point are inversely proportional in here. So vapor pressure goes up and boiling point goes down. And the example that we might have here is, let's take a look at methanol, which you have heard of, versus water, which you've also heard of. Okay, so methanol has a vapor pressure of 108. Okay, so methanol has a vapor pressure of 108 and a boiling point of 64.96. And then water has a lower vapor pressure of only 19.8, and then a higher vapor boiling point of 100. So this one went down, and then this one went up. Let's take a look at surface tension now. In surface tension, surface tension is a liquid's response to the imbalance in the attractive forces and the tendency to minimize energy that creates spherical shapes. And that's because spherical shapes have the greatest volume with the least surface area. Uh, Stronger attractive forces result in greater surface tension. Okay, so then we have to think about what are those attractive forces, and we have two of them. We have cohesion forces, and cohesion forces are liquid-liquid interactions, and this means that the liquid sticks to itself. Okay, and forces, we have liquid solid interactions. And in this case, the liquid sticks to its container. Stronger adhesion forces result in a concave meniscus like this. Okay, and that's what water does. And then stronger cohesion forces result in a convex meniscus, and that means that it comes over like this. And mercury has a convex meniscus. So that means that water's adhesion forces are stronger and it travels up the side. This also affects your capillary action. All right, so now let's take a look at polymers. Polymers, now remember, you can review our polymers from chapter 2, I believe it was. Okay, so go back and look at your notes from chapter 2. That's where we worked through all of the steps of creating a polymer. But now what we're going to do is we're just going to give those steps some names. So polymers are gigantic molecules constructed by stringing together smaller molecules called monomers. We made polyethylene, remember, back in chapter 2. The physical properties of our polymers depend on the monomers used, their reaction types, and any catalysts that we use to prepare the polymer. The steps to creating polymers from monomers lead to what we call free radical addition reactions. Okay, and they form a special type of polymer called an addition polymer. Again, I showed you each one of these steps back in chapter 2. And the steps, though, are actually called initiation, propagation, and termination. All right, so let's look at these. In an initiation period, a free radical is produced. In propagation, the free radical attacks the double bond of the monomer to break the double bond, and this leaves a single bond and a new free radical. Okay, so remember, in order to do these, you actually have to have double bonds involved. If you don't have double bonds, you would be using a different type of process. Okay, so this continues. This just continues on and on and on. This continues on and on, we'll say, until termination occurs. And this is when a free radical reacts with another free radical. This stops the propagation. And because of that, sometimes it's also called chain termination because it terminates the chain, not just the process itself. Termination is random. So what happens in this case is that not all polymer chains have the same length. Basically, it happens whenever the free radical and another free radical come into contact. So if it happens early on, then you have a shorter chain. And if it happens after time has passed, then you have a longer chain. And so one of the things that you need to do then in industry or in polymer work is that you need to have a way of separating out your long chains and your short chains. Okay, so we have one more slide here. Okay, and let's take a look at some different forms of our polymers. The first one here you can see is something that is called isotactic. Okay, so this goes with A. This is our isotactic polymer. And in this one, all of the methyl groups, and these pink ones here are your methyl groups. All of your methyl groups are arranged on the same side of the polymer chain. So here you have all of your methyl groups up here. And then just to identify it, here in the middle, you have your carbon atoms. And these little ones down here on the bottom are hydrogens. Now you have in B, you have a syndiotactic polymer. So this is our syndiotactic. Okay. And in this one, your methyl groups alternate systematically. So every other carbon, they're either on the top of the chain or the bottom of the chain, and they switch sides opposite. And then the hydrogens switch sides as well. In our last type of addition polymer, we have an atactic group. And in an atactic polymer, the methyl groups are randomly arranged. So they might be here, and then you might have two, and then they might alternate, and then you have a couple here. So there's no pattern, okay? So both A and B are highly patterned, and in an atactic group, you have no pattern for the position of your methyl groups. All right. Good luck. I will see you in class.